So welcome to the last talk of today. It's my pleasure to introduce Patrice Le Calvez from Institut Mathématique de Jussieu, who's going to talk about area-preserving surface homeomorphisms with no horseshoe.
Thank you. So the last time I was here was 6 years ago. There was a Brazilian-French conference. And the first time I went is in '88. It was just 1 year after I finished my thesis. And Palis invited me to spend 4 months here. He gave me the opportunity to make a mini course and also to publish this mini course in a very new review, a journal, a Brazilian journal, was Ensaios Matemáticos. I spent, in fact, it was a wonderful experience to spend these 4 months in Rio. It has followed but a lot of visits in Brazil, but not only in Brazil, but in South America, and a lot of collaboration. And this is one of the collaboration. I'm very happy to be here, and I would like to thank a lot the organizers. Okay, so this is a joint work with Pierre-Antoine Guilleneuf from Paris, Alejandro Paseggi from Montevideo, and Fabio Tal from São Paulo. Okay, so the problem is the following. We want to understand the dynamics of conservative homeomorphism of the surface, which have no entropy. I have written here no horseshoe, but in the talk it will be no entropy. It's about the same. Okay, so during the talk, S is a connected oriented, closed surface, closed means compact with no boundary. Okay? So I will recall some facts concerning flows. The fact one is the following. A time-one map of a flow on S has 0 entropy. In fact, I think it's one of the first papers of Lysan-Young. Maybe it was known in the Russian school, I don't know, but it seems that it's one of the first papers of Lysan. Okay, so when you have a flow in the surface, there is no entropy. Okay, there is a fact two, so there will be an example of a homeomorphism with no entropy. The fact two is the following. If the flow is non-wandering, there is no wandering orbit, then there exists a decomposition of the dynamics of the surface in transitive pieces, finitely many transitive pieces, and annular pieces made of periodic orbit. Okay, this begin from some result of Mayer in the 40s, and there is a lot of mathematicians who have worked about the dynamics of area-preserving diffeomorphic flows on surfaces. There's a lot of literature about that. Roughly speaking, I will give you an example. I will give a more precise result after. Let's go on the torus like this. We begin by an irrational flow, and we will do two things. We will do something like this. Okay. I have added what's that like this? I have a saddle point here, two saddle points, and two elliptic point, and your flow is like this. And I can, so you have singular point of the flow, 4 singular points. I can put also two stopping points here on the flow. And here you have an example of a null representative flow with non-wandering orbits. And you see that there is 2 annular regions like this, which are made of periodic orbits. And there is, outside this disk, there is a pieces with genus 1, where in fact the flow is transitive. And this is an example that all the conservative flows on surface look like this. Okay. So the problem is, do there exist such decomposition result when you replace a flow, or time one map of a flow, by a homeomorphism which has no entropy, and which is preserving or conservative? And this is, we will see that yes, in fact. So for that, I have to continue about some facts. The fact 3, they concern homeomorphism. I say the following. If F is a homeomorphism of F's as 0 entropy, then exists an integer Q such that FQ is isotopic to the identity, or to a dent-twist map, H. So what means that H is a dent-twist map? It means that there exists a finite set K. There exists a family AK star of closed annuli such that for restriction H restricts to H is conjugate to tau to pk, this is an integer, where tau is a map which goes from the annulus in itself, defined by the following formula. I mean, you have something like this. You have an analysis like this. And like this. And when you take the image of an horizontal like this, okay, the image, it's something that turns like this. It's a twist map. It's a twist map of the annulus. So it's an identity here, it's an identity here, but you have a twist inside. So the map H is like this, and H is the identity on the complement of the K. Okay? So you have such a situation. For example, you have 3 annulus like this. The map H is equal to identity here, and on each annulus, it is a polar of tau, a certain polar of tau. Okay? Now, this is a consequence of Nielsen-Thurston classification theorem. In fact, when you have a homeomorphism of a surface, you it is isotopic. You can decompose it in what called irreducible pieces. And irreducible pieces are separated by twisted annulus. And in these pieces, it can be periodic or it can be a pseudo-Anosov map. But if there is no entropy, there is no pseudo-Anosov map in the Nielsen-Thurston decomposition. And saying that it has not pseudo-Anosov map means that by taking a power, either you are isotopic to identity or you are isotopic to such a map. Okay, so if you want to study Hurry preserving surface homeomorphism with no entropy, you must be in this case. I will give you another result concerning the homeomorphism is the following. I will suppose here that F is isotopic to identity and the genus of S is at least 2. Otherwise, there is something similar which is true, but I suppose this. I suppose that if the topological entropy of F is 0, then if mu and nu are invariant finite measure, we have the intersection of the rotation vector of nu and nu is 0. I mean, the rotation vector invariant measure never intersect. So I will define a little bit more. So this is an homology class. And this is a classical intersection form on the first homology group. When you are considering as classes loops, it's exactly the algebraic intersection. This is due, in fact, it was proved by Katok for flows, and for maps, it results, it's a thesis result of Gabriel Lelouch. And in fact, it generalized something which was known for the torus, and Alejo spoke about this in his talk, was by something of Yi by Macri for the torus. Okay. So let's define a little bit more what is the rotation vector. So you take I, be an isotopy, isotopy from identity to F, and define I of Z so this is a loop. You have a point Z, you follow along the isotopy, you have a loop. But if you look at this object, it is a loop. No, it is path. But you can see also as a linear map of the set of closed one form. In fact, it's not a current because it is not necessarily differentiable. So you cannot integrate a one form on something which is only continuous. But you can if it is closed, because you can approximate this path by a smooth one, and if you make such an approximation, such two approximations, you will get smooth paths which are homotopic. And so if you applied a closed, or if you integrate a closed form, you will get the same value. So there is a way to define the integration of a form like this. So this is a linear map on the set of one closed form. Okay? But you can do, after you do this, you can integrate relatively, and you still get a form on this. Okay? You just integrate relatively to mu. In fact, if you fix I, and if you integrate one form here, you get a continuous function of z. So you can integrate relatively to mu. And you will get a continuous function, an object which is dependent linearly on the one form. And this vanish on the set of exact form. Because when you have an exact form, and you integrate an exact form on a loop, if you have a primitive, it's the value of the primitive in f of z minus the value of the primitive in z. So when you integrate relatively to mu, because mu is invariant, it's 0. Okay? So in fact, it is a one form on the set of the space of closed form that vanish on the space of exact form. So it is a linear form on the first cohomology group. Okay? And what is the set of linear form of the first homology group? You know that it is the first homology group. Okay? So in that way, you define an homology class when you have an isotopy from this, when you have an even measure. It's easy to say that when you have two isotopy, we trace two different isotopy, because the genus is bigger than 2, these paths are homotopic. Okay, because the pi1 of the set of homeomorphisms is trivial. And so this doesn't, it doesn't depend on the choice of I, neither this value. Okay? As a path, it depends, but not as a form. And so you have defined, it's called also an asymptotic cycle. So the theorem tells you that if you have two asymptotic cycles that intersect, there must be entropy. Okay, so what we want to prove, to get is a result which doesn't work for measure, but a stronger result with all points. Okay? So now I will state the theorem. So maybe before stating the theorem, I will give another example, maybe here. I will draw another figure of a map which is a map which has preserved which is conservative and which is not a flow. So I consider this. Here, the dynamics here is the gradient dynamics. So you have, it's a gradient of height. Okay, you have. So the dynamic is the dynamic of the flow here. Here you put the dynamic of the flow, but you change. It's not the height, it's minus 1. And between, I will put an elliptic beard, something which looks like an elliptic beard. So I will consider something like this. It's not easy to draw because there is something behind. I'm not a specialist of drawing things which are behind. There are people who can. I cannot. And here you have a periodic point of period 2, okay? And here you have, you see, this looks a little bit like the dynamics of a Beard flow on an ellipse, Okay, and you have glued. This is not a flow because there is isolated periodic point of period 2. For a flow, you never have periodic points which are not isolated, which are isolated. Okay, but this is a represerving. Okay, so now we will state the result, the theorem. Third theorem. So I have my surface. I suppose that F is a homeomorph F. Orientation preserving, maybe. No, isotopic, yes, because isotopic, we suppose, such that. Okay. So with four conditions. F is isotopic to identity or to a dentist map. In fact, because of this result, which doesn't exist anymore, it's sufficient to look at this case. I suppose that F preserves a finite measure, Borel measure, lambda, of total support, and particularly F is non-wandering. I suppose that the topological entropy of F is 0, and I will suppose also that the set of fixed points is not empty. This is to include the case of the torus in the theorem. If F is not a torus, this is always true. But if it's a torus, I have to add this condition to get not empty. Okay. Otherwise, there is only the case of the torus, it's never true. Okay, then there exists a decomposition S A union B union C such that, okay, we'll begin here.
What did you say that
it's not a flow.
It's not a flow, so what is it?
It's not a flow because there is two reasons why it's not a flow. The first one is that these are periodic points of period 2 that are isolated. When we have a flow, if you have a period, if it's not fixed by the flow, when it's periodic, there is a curve of periodic point with the same period. Yeah. You cannot have isolated periodic point. Okay? So it's not a flow.
Yeah, but then I don't understand the picture. How is the dynamics?
The dynamics is like this. It's integrable. It's completely integrable. You have a lot. You see, almost all the points, the orbits are on circle, except separatrix. But it's not a flow. Okay, you have periodic objects. For example, this is a periodic object. In flow, you have not such periodic object. Okay, so such that first A is a different union of annuli where the AI are the maximal fixed point free annuli. Fixed point free annuli. Okay. And here, for example, the annulus, we have one annulus here, one annulus here, one annulus here, one annulus here, one annulus here. Here you have one annulus here, an annulus here. So it means that there exist objects which are the maximal fixed point free annuli. It's not clear that such an object exists. B well, the Bj are the maximal irreducible fixed point free irreducible fixed point free irreducible sets of genus positive. What does it mean? It means the following. Bg is a connect invariant open first, and for every B, there is no B, connect invariant open with B contained in Bj and genus of B smaller than genus of Bj. You cannot find a pieces inside which is connect invariant with genus smaller. It's kind of irreducible, and after you can define maximal irreducible sets. Here there is no, of course they have positive genus, so necessarily G is finite, because every Bg has a genus. In this situation, Bj is exactly this set. You take out these 2 points, and you look at the others. So here you have AI, the union of these two annular, and Bj is what is outside. And C, what can you say of C, which is a complement? C is closed. A and B are open, C is closed. All the fixed points of F are in C, and every point in C is fixed or heteroclinic. Okay. So the points which are in C must be fixed, or the alpha limit and omega limit are inside. It corresponds here to this point. Is this drawing? Okay, in green, I have, in green and blue. Green and blue gives what is C. Okay? So we really have a decomposition of Euler pieces, pieces of genus positive, and so let us continue. F, for every J, F restrict to Bj is transitive. So the Bj are transitive. And 5, for every I, there exists a continuous function invariant rho, which go from AI to 0, 1, AI to 0, 1, such that rho of Z is a rotation number of Z in AI, and it's an annulus, so the rotation number is really the speed where the guy turns in this annulus. So it's nothing to do with this. It's much more simpler to define. And rho Z tends limit belongs to 0 or 1 is Z tends to a non-trivial end of I. What means a non-trivial end? This is an I. There is two ends. One which corresponds to this fixed point, and one which corresponds to this boundary. Okay? This end is trivial. The impression of the end is reduced to a point. But this end is not trivial. The impression of the end, when you take a sequence of this, is conversion to something which is not a point. And it means that here the limit must converge to 0, 1. Of course, there is nothing, no result about what is the limit, because if you have an elliptic point, for example, which is irrational, the rotation number will tend to this rotation number. So for ends which are trivial, there is no such a result. So it says when you go to the boundary of the annulus, if it's not reduced to a point, the rotation number tends to 0 or 1. Okay? And so what does it say? It says that here, the annular I are foliated. There is a kind of foliation. It's not a foliation. It's not curved. On the drawing, it's curved, of course. But it can be pseudo-circle objects, very much more complicated topologically. But there is a kind of partition in the annulus, a kind of foliation in pieces like this. So it really looks like in the case of flow. So I will continue. There is another one. Okay, suppose here that we are in 6. Suppose that F is isotopic to identity and the genus of S is at least 2. Otherwise, it is also good that you have, as I explained, on any definition of rotation vector, we suppose it. If let mu be an ergodic measure, probability measure, there are 3 cases. Mu is a Dirac measure at a fixed point. This is a possibility. Otherwise, there is another case. It is that the rotation number of mu has a rational slope. Okay. And there exists I such that mu is supported on an element I. And in that case, it is not, it has an irrational slope. And in that case, there is J, which is, that means this set, all the invariant measures are either supported on fixed point, ergodic measure, or in annular when the rotation vector is rational, or has a rational direction, or in this part when it has irrational rotation. So you really can say about invariant measure where they are in this decomposition. Okay, and so there is another one, which is that if F is homotopic to a dentist map, I is not empty. In fact, there is as many invariant annulus that there is invariant twist annulus for the dent twist map with their multiplicity. You know that must be invariant annulus in the case you're dentist, homotopic to a dentist map. And to finish, let's say the following. If you take for every Q, you can look at the set for FQ. It is contained on the set of F, but the set of BQ is always equal to B of B. That means when you will, in this example, for example, when you will look at FQ instead of F, you will have to take out all the fixed points of FQ. So you will have all the periodic points which were in the set A or F are now outside A or F. You take out the periodic point. So you will get annulus more and more small in size. But for the irrational part, it doesn't move. It's stable for all iterates. So for example, here you see that when you will have, we'll go to the polar F2, you will see new decomposition in annulus. For FQ, you will have more annulus because you will have here one, another one, another one, another one. You will have one more. Okay, so in fact, this is the theorem. So I want to make some comments. I will not have the time to give any element of proof, I think, but I want to give some comments. Okay. So it was known for flows, as I told you before, in fact. It was also known if the genus of F is 0. I mean, if S is a two-sphere. In fact, it was known, it was a result of Franks and Handel. If F is smooth, it's infinite, and lambda is an ariform. So you must have smoothness in their proof. If you use Yomdin theorem concerning entropy or things like that. And we gave a proof with Fadotal through if F is C0, and you can replace the fact that it is Hurry preserving by saying that every point is non-bounding. Okay? And in fact, here in the present theorem, the theorem, in this theorem, we can probably replace F preserves lambda by omega F is equal to S. In fact, we met in China two weeks ago, and we discussed, and except this point, which has to be proved, the rest can be proved also in the case you replace a preserving a measure by no wandering point. I will make some other comments to see, it's not the proof, but it will explain you what happened. In the case, if you are in a sphere, no, 0. We can do the following thing. There is a way. We can explicitly say, well, who are the AI? In that case, because it is not fair, there is no BG. Okay? There is no BJ. There are only AI, because there is no genus. So you define the set. W is a set of points that exist a disk, topological disk, D, open disk, such that Fd, this disk is empty, and the set of points K is at least 2. That means these are the points Z such that the orbit meets a free disk at least twice. It's easy to see that W is open and invariant because it's a result of orbits. You want an orbit to meet a free disk at least twice. And if you write W in connect component, okay, these are connected. In fact, the AI, of course, these are disjoint, and so these are nothing but the interior of the closure of the WI. Okay, when you have such a decomposition on an open set, if you look at this family, it will still be disjoint. And these are the annulus. So it's very easy to see how are the annulus in this case. So I will try to explain how you construct the annulus in the case the genus is bigger than 2. Okay, suppose now that the genus of S is bigger than 1, 2 maybe. No, 2. Let's say 2. Let's say 2. Okay. So you know that the set of recurrent points is contained in A, in B, because the points which are not in A and B are fixed or are the omega limit and alpha limit are make or fixed point. So the recurrent points are in A or in B. So or you can decide who is in A, who is in B. There is a very simple property. You take a recurrent point, and you take a disk, a free disk, that contains Z. Okay, you have your point Z here, you have the surface. You consider E an isotopy. From identity to F. And you take a recurrent point, and you take a small disk D, and now you can look at the first photon map. You look at Fn is the first return. Okay, so this point Z here, come here. Okay. And you come back here, and you consider now the loop gamma, which is you make the concatenation and after you finish by choosing a path which is in D. So I follow along the isotopy, I have a path, then I follow, and then I follow. And then I follow, you have here, and after I close with thermal pieces. Okay? Doing that, I can find a loop. There is two possibilities. Okay, so either there exists a disk D such that the homology of gamma is orthogonal to the rotation vector of lambda. Okay? Remember that you have an even measure. You can look at this rotation vector, And suppose that the homology of gamma is orthogonal. Then Z is in A. If for every D gamma is not 0, then Z is in B. So you know to be in A means that when you take a disk and when you come back, the homology that you find is orthogonal to the rotation vector lambda. Being in B, it's never orthogonal. It's something that you have probably already seen for flows if you have given in a course a proof of Poincaré-Bendixson theorem. Let's explain what happens in the case of flow, and I will finish by that, because I will not have the time to give. Well, but to explain this, suppose you have a flow. This is a very classical thing. Suppose you have a flow. So the flow, when you have the flow, you have things like this. So what you will do with the flow, you take a point Z here, and you take a transversal of the flow. You take a transverse path. The transverse path will play the role of the disk here. It will play the role of the disk. So you suppose this point is non-wandering. So if it is non-wandering, it will come back in a certain point that we'll call, no, this is Z prime. Okay? So you have your point, you follow the orbit, and you arrive here. And so you can close exactly in the same way by, you can construct gamma Z exactly in the same form. Except that closing in the disk, you close on the section, on the transverse section. But you know that if Z prime is different from Z, it implies that gamma Z lambda is non-zero. Why? Suppose you have such a point. It's something you have already, I'm sure you have already observed already this. Instead of taking this path, you can choose another path like this, you see? Okay, you start from Z, and you arrive here, and this is transverse to the flow. But instead of taking this point, you can follow this point and arrive exactly at Z. It means that you can construct, if Z prime is not Z, you can construct a loop which is transverse to the flow and which is homologous to this. Okay? But if it's transverse to the loop, that means the rotation vector is not 0. It's impossible that it's 0. There is a section. Everybody intersects this section. Okay? So if you have this is equal to 0, there is a unique case which is possible. So if gamma Z equals 0 implies that Z is periodic. Z prime equal to Z, and Z is periodic. So you see that periodic points are the points that you, when you make a return map, you fall exactly at the same place. Okay? And non-periodic point is a point that you cannot find. When you have an irrational flow, when you take a section, when you come back, you find the good approximation of the irrational slope, but you never fall on the slope from one side, from the other side. Okay, so we finish by this. I have no time to give idea of proof, but there is a moral that you have point of irrational type and point of rational type, and you can really divide dynamics into the rational type points, which are exactly like periodic points, and the other one, which looks like we have results concerning the transitive pieces, but they are not so clearly done, so I prefer not to talk about. And I will finish with this. Thank you very much.